Okay. Hello. Thank you, Dylan. Um, we're back to the ear pods because I am listening to music rather than being present with you. That is not true. We're trying to do another recorded section without DCE to record section. Um, I'm realizing that I'm not sure that it was announced, but the fifth problem set, the shell problem set, was released on Friday. Did anybody actually notice this? Uh-huh. Great. We think that this is a fun one. This is one that will have a feeling that's somewhat like problem set one, in that we have a whole heap of tests, and you're going to make those tests work one at a time. You're going to work through the problem set from the beginning to the end, making the tests work one at a time. And so this section is about a couple of subjects that relate to this problem set. One of them is a specific code structuring topic. One of them is has to do with the meanings of grammars, and then there's a bunch of exercises that just have to do with the way shells work. So the exercise portion will go through, I think, last after an initial period where we do one exercise together, one or like probably about three exercises together, and then I'll switch gears. But before that, are there any questions in general about shells? Okay, great. So the code for this, problem set, or the code for this section, is in the SO7 directory of your CS61 sections repository. And so what we're going to use these for, our goal here is to help you understand the way that the shell tests are written. So the shell tests are written in this sort of, they are shell commands, but like sometimes you will get stuck on a test and you won't understand what the test is doing. And if you have some familiarity with shells, which we know not everybody does coming in, then you'll be able to write your own tests and actually validate what your shell is doing as opposed to others. Yes,
Jiho.
Jiho.
Yeah, I actually had a question about shells from lecture last week.
Okay, question about shells from lecture.
This was from fork mix file.
Uh-huh.
And it was like the one where you called fork before you actually opened the file.
So we're at fork mix file, calls fork, and then opens the file.
And
yes.
that's the one where like the two different like processes that kind of like battle each other out in the file.
Yes.
And I was wondering about like why exactly it was that like the expected number of characters was or the actual number of characters was half the expected number of characters in
right.
particular instance.
So let's see if I can't pull this up. Nope. Okay. So we're looking at process one, fork mix file.cc. So we didn't actually look at the result of this particular program. But if I were to run this program, we would see that in fact this program does have what we say it has. So this program prints what? Prints 1 million copies of either baby or mama. So given that I'm sorry. I'm not sure that we're understanding things correctly. Okay. So if I run this program, I expect that we will get an interleaving of baby and mama, and it will be 10 million characters, not 5. So you're talking about the version which is discussed in the lecture notes, but was not discussed in class, where I take this opening of the file and I put it after the fork, like this. And what we saw when we ran this, and we'll see how we get this video edited together, if at all. What we saw when we ran this, well, we didn't see anything, so let's run it. I'm going to make Going to change to the directory and make fork mix file. Get an assertion because I need to give a file name. So just put it in F. And F, in fact, has only 5 million characters. So let me draw a picture of the difference between what was happening when we opened the file before the fork and when we opened the file after the fork. So the way that these pictures are drawn for us, we put user processes above the line and kernels below the line. This little dingus is a file descriptor table that says where the file descriptors are opened. The file descriptors 0, 1, and 2. 0, the standard input, is open to the keyboard. 1 and 2 are open to the console, right? And I'm differentiating these because the standard input is usually open for reading, and the standard output and error are open for writing, the writing to the screen. In fact, these are all opened read-write, but that's like a preview of, that's so that you can't say that I always lied to you. But I think it's more helpful to understand it this way. So here's our fork mix. And in the version where we open before fork, so there's an fopen and then fork. So the fopen creates a new file descriptor that points to a new file object. The file object is what contains the file position, okay? So here's that new file descriptor. It's 3, because that's an unused file descriptor at that time. There's the file position. So I'm going to put the contents of this file in this long, skinny rectangle down here. Okay? So the file position is originally pointing to the beginning of the file. It's the file F. Okay, fork occurs. New file descriptor table. Standard input, output, and error point to the same objects, to the keyboard and console. And file descriptor 3 points to the same file structure, which has this single file offset, just one offset. So if I were to look at F in the old way, I'm going to go back to the handout version. Fopen and then fork. Run fork mix file on F. We're looking at this. No, thank you. Okay, we see a bunch of mamas. Eventually, we will see some babies. We see a mama baby. We see at least 4,096 bytes worth of baby, because the deal here is that because of standard I/O buffering, an entire standard I/O buffer's worth of characters is being sent to the kernel via a system call. The system call is atomic, but the system call is going by 4,096 bytes, not by 5. So we see a bunch of babies, then we see a bunch of mamas after a B. So every write here, you get a write to this file descriptor. That writes a bunch of mamas and updates the file position by 4,096 atomically, meaning that the data is written and the file position is updated as one step, and nobody can get in between. Okay? Then maybe the baby does some prints. So that prints baby, starting at position 4,096, and then updates the position to 8192. Maybe the mama wins then, maybe the baby wins then, maybe the baby prints another 8192. But you can see that no individual file position in this file is used more than once, because every update to this file uses the same file position and updates that file position atomically with respect to all other writes to this file. Okay? So that's fopen and then fork. Now let's do fork and then fopen. That picture is quite different. When I say quite different, I guess I mean almost the same, but different in a really important way. Fork and then fopen. So at the time of the fork, there's only 3 file descriptors that have meaningful values in the parent. So only those 3 file descriptors are copied to the child. Fopen happens in both the parent and the child. Because the parent and the child start from clones of the same state, they're going to choose file descriptor 3 for their F file. They're both going to choose file descriptor 3. So if we looked at the S traces of these 2 programs, they would look extremely similar, right? Where this S trace started at the point of the fork. So after the fork, the S traces would look extremely similar. Like the same file descriptor number would be there. Just the contents of the data written would be different. But, and this is critical, both of these files, these are different files that point to the same, sort of like collection of bytes in memory and on disk, but they have independent file positions, not the same file position. So now, mama gets written, we get one write system call to file descriptor 3 from the parent file descriptor. That writes mama and updates this file position to 4096. No problem. But when the baby writes, the baby is going to update a different file position. That file position hasn't been modified. It's still 0, like it was when the file was opened. So that overwrites this data with baby data, and then sets this file position to 4096. It's unlikely that we will get only mama or only baby in the output, because they're sort of in a race. But every file offset in the actual file data will be written twice. Be written by one of the processes and then overwritten by the other. And so the total length of the file will be the same both times. 5,000 bytes. Both times, right? These are happening concurrently. But neither process writes more than the other. They both write exactly 5 million characters. And so you're going to get 5 million characters in the output. Any questions about this? Maybe we should verify it quickly. This, I'm not sure. Maybe the baby completely won. Nope, the baby did not completely win. They were in a race. But there's exactly 5 million characters in the file. I have a picture in my head like this, like a carnival game involving 2 rabbits who are trying to win a race. And like in the region where the blue rabbit came first, then the file will be red because the red rabbit comes afterwards and sort of like poops red on the file. And then if the red rabbit happens to overtake the blue rabbit, then the next portion of the file will be blue because the blue rabbit comes second and poops over that portion of the course. But the race course is the same distance for both rabbits. Analogy. Okay. Yes.
Sorry, what is the 4096 box representing exactly?
That is the file position. You remember file positions from the last problem set.
It's not stored with the file, it's stored by our process.
Yes. Every different instance of an opened file has the same file position, even if those are like different opened files referring to the same file data. I can see that did not work. But if you think about it, it would be very horrible for this to be any other way. Let's say that there was a very popular file on your file system. Maybe it's user shared dict words, right? Like the list of all of the words in some dictionary. And let's say that all of the different versions, whenever anybody opened that file, they got the same file position. Everybody shared it. It would be impossible to read that file, right? It's like if there was, if instead of, this isn't a great analogy, but if like every time you loaded a web page, you got the version of the web page that just had the stuff that no one else in the world had read yet. It would be really very difficult to deal with that. So it's a sense part of process isolation that when you open a file, you get an independent file offset from the rest of the, from the other instances of that open file in the system. So if one process opens the same file name twice, obtaining two different file descriptors for that file name, those two file descriptors have independent file offsets. File positions, excuse me. Alana? Adriana, sorry. Sorry?
When you open the file, isn't the file position zero?
When you open the file position is 0, if there is a file position, right? If you open a streaming file, there's not really a file position because you can't seek or anything. When you open a file, the file position is 0. But it's important to remember that when a process starts, it already has some opened files, right? It has its standard input and output and error, and it has any other files that were opened at the time of the fork. And so those files, their positions might not be 0. More questions? Okay, section, material. We're in the SO7 directory. Use only shell commands to print the content of evereturns.cc and evil.sh into the console in that order. Do y'all know a program that prints a file to standard output? It's named after like Hello Kitty, right? Cat. Cat, which is like the silliest, it's one of the silly Unix command names, but cat is the name of this program. So if you want to know what the cat program does, you can type cat -- help. When you type -- help after a command, you often, not always, but often, will get a brief output that explains the kinds of arguments you can give to the command. If you scroll up, there's usually a one-liner or a short description of what that program does. So cat concatenates the files to standard output. So you give it file names that just takes those files and writes them to standard output. It does have some options that nobody ever uses. So if I typed cat evereturns.cc, and then I typed cat evil.sh, I will have answered the exercise. Simple, 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 simple. So that's exercise A. So let's get familiar with a couple more examples of shell syntax. Many of you will have used these before because we sort of use them informally in the rest of the course and just in your everyday life. So what redirections do is redirections, according to this picture, redirections change the initial state of a program by changing what its standard input, standard output, and standard error point to at the time that the program begins. So normally a program standard input, output, and error are all pointing to the keyboard, the console. But if a program is started something like, instead of echo hi, if you say echo high greater than f, that will take the program echo high and it will run it in an environment where its standard output is redirected to a file named f. So pictorially, what that will do is instead of having this arc where the standard output points at the screen, we have another arc where the standard output points to a normal file that's associated with the file F on disk. 0 there is the file position. Okay, so redirections are about changing the environment of the process before the process begins. There's something extraordinarily powerful about this. It's also unlike the way things like redirections are handled in some other operating systems. So at least historically in Windows, redirections were handled by the process itself. So we can redirect the standard output with a greater than. It looks like an arrow. You're sending the results into a file. We can redirect the input with a less than. You're sending the file into the program. And we can redirect standard error by giving a number. So standard error on the shell syntax that we use, standard error is 2 greater than. So 2 there just means standard error because it's always standard input is 0, standard output is 1, 2 is standard error. Okay, so if we run these 3 commands, if we say echo hello kitty, that just prints to the console. If we say echo hello kitty to see it, output to cs61.txt, the standard output doesn't get anything. If we do cat from cs61.txt, cat, if you give it no arguments, reads from its standard input and writes to its standard output. So here, because I've redirected the standard input of cat from the file, it's reading the contents of the file, then it reaches end of file, and it prints the results to the console. Okay, we have a question here. What effects does the second echo have? I just told you. It makes a file called cs61.txt that contains the output of the echo command. And the cat command is printing hello kitty to the screen. There's questions. Jalen.
Third one, why do you need the redirection?
You don't need the redirection. If I just did, so the question was on the third one, why do you need the redirection? And the answer is that you don't. If I just say cat cs61.txt, I get the same result, but I'm getting the same result in a different way. How do you think I could figure out what the difference was? Thank you. So I'm going to strace into s1 dot, out cat in from cs61.txt, and I'm going to strace into s2 dot out cat cs61.txt. And we'll look at s1.out first. It's a relatively short strace. There's the end of the strace. Does it look like cat is using standard I/O the way you all did? How is cat trying to optimize its input-output relative to what you saw before? So that nmap with a null is not actually reading from a file. That's like a version of malloc. But it's reading more than 4,096 bytes, right? It's reading up to 100 kilobytes, 131072. So cat is highly optimized for its purpose of reading a file and writing the same file. Okay, so that is that version. Let us look at the other version. Get to the end. What's different? Yes, Jiha.
The file descriptor number for reading is different.
The file descriptor number for reading is different. And if we scanned back through this, we would see, and in fact, here it is. This is the second version, the one that has the file as a command line argument. We see that that file is explicitly opened by this program. I can't reach it, but it's right up there. It's open at cs61.txt. Okay? So this program was given an argument, and it chose to interpret that argument as a file name. Another program, if I just said echo, it wouldn't interpret that argument as a file name, but it would just print cs61.txt. This program it doesn't know what cs61.txt is. I just searched for cs61 in the strace. It's not there. This program just uses the standard input. It doesn't open anything. It uses the standard input, which it assumes is already open. Okay? It is possible, if you're, say, writing a shell for the purposes of a problem set, to mess up your shell and run a program in an environment where it has no standard input, where the standard input is just closed, and all attempts to read from standard input return an error. And it's kind of fun to do that and see how many Unix utilities are deeply unhappy with such a situation. Standard output also. You can run a program with no file descriptors at all. Okay. Good question. Thank you. So there are other kinds of redirection. A particular kind of redirection that I want to highlight is if you do 2 greater than signs instead of 1, that appends. And what that means is that every write to the file will go at the very end of the file, regardless of what's happened in the meantime. There's also this funky one where we say 2 greater than ampersand 1. And you may have seen that in when I'm doing lecturing. This is something that I actually frequently use, even though it's like, it basically, you know, I just know what it means, right? You have to think of it as like a magic word, like open sesame. What this does is this says, take the standard error and use the same file descriptor that you're currently using for the standard output. So send the standard output and the standard error to the same place. So let me give you an example of what that might do. So here's the yes program, right? Yes. Just prints a lot of yeses. If I want to see all the yeses that it prints, I pipe it to less, and then less paginates the yeses. Here's a program that causes a bunch of errors. This causes an infinite number of errors. Don't run that yet, please. So if I say sh ono.sh, it's going to print a bunch of errors. But it prints those to standard error, not to standard output. So if I try and look at all of the errors by piping the output of this command to less, what I see is something terribly nasty. Less is just blocked and is showing me nothing. But I'm getting all the error messages anyway, because they're being sent to the console, which is not being paginated. So I can control that by saying, take the errors, which is file descriptor 2, and send it to the same place as you're sending the output. Now the errors in the output go to the same place, and the errors are paginated. So this makes the output harder to read because it's interleaved with errors, but in a situation where you have a lot of errors, it can be quite useful. Yes?
Why are errors in file descriptor 2?
Errors are on file descriptor 2 because file descriptor 2 is the standard error. That's where that's when you print a stderr, it always goes to file descriptor 2. Okay. So I encourage you to do these exercises if you're feeling at all uncomfortable with the shell. We'll do pipes in a bit, but I think at this point, it makes sense to switch to point out what's in the documentation and references, and then switch to going through some problem set specific stuff. So in the documentation and references, we have a list of a bunch of useful programs. This is not a complete set of useful programs because there are hundreds of useful programs. And it's like having a large vocabulary. It's pretty fun to know a bunch of these small Unix useful programs. I don't know a huge number of them. But this is a good set of them. It's useful to find out about them either by reading their manual page. So you say man and then one of these. Or by running the command name with -- help. So we've already seen cat. You've seen WC, which I use to count words and characters and lines. You've seen head and tail, echo. True and false will come up later when we do conditionals. We've seen sort, unique, and we saw TR on Thursday. Now let's talk about the grammar for the shell that you're going to implement. How many of y'all have seen Backus-Naur grammar before? Something that looks like this. Very few people. Okay, that makes sense. That's great. We're going to talk about how to interpret this. So a Backus-Naur grammar is a declarative way to describe a language. And a language in this context means essentially a set of strings. A string is in the language. A string is like a valid sentence in the language if you can obtain that string by following the rules of the grammar. So I'm going to now open up. This is all just going to be text work, but I think it'll be useful. Just going to work through a bunch of examples of different very simple grammars. So first, we're going to do the empty grammar. So our desired language should have no valid sentence. And this is relatively easy to write in this grammar description form. So every Backus-Naur grammar has what's called, what I'm going to call the top symbol. It's the root symbol. And the root symbol is the thing that defines what's in the grammar and what's out. So if something matches the root symbol, which can refer to other symbols, then the resulting sentence is in the grammar. And if you can't find a match, then the resulting sentence is not in the grammar. So there's my language. It says that there is no valid sentence in this language because nothing matches shut up. Next, instead of an empty grammar where there's no valid sentence, we're going to have like let's say we'll call it the children's grammar. So the desired language is that only empty sentences are allowed. So children should not be heard. So for this, we again start off with a root symbol, with the root non-terminal. But now I'm adding a new feature to this grammar description language. This says empty string. So this language, unlike the language above, has one valid sentence, and it's the sentence that consists of the empty string. Okay? So anything that, any string, there is no string that is a valid shut up sentence. But there's one string that's a valid child sentence. It's the one that's empty. Okay, next, letter grammar. That's what I want the desired language to be. Any ideas how I might write this? Yeah, Catherine.
Lowercase a or b or c.
Great. Lowercase a or b or c or d or z. So this is a totally fine grammar that has the desired result. Here's another one. I'll put this into the section notes somehow. It's not in there now, but it'll get in there. So in this alternate one, we give multiple rules that can any one of these rules can be used to satisfy the letter 2 non-terminal. Same thing. Okay. Now let's get a little bit more complicated. So now we're going to have the word grammar, desired language, a single word of lowercase letters. So I want the empty string to not fit this grammar. It's not a valid sentence in this language. But I want A to be a valid sentence in this language. AB, ABC, Z, 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 Z. So how can we do this? This is one of those cases where we use like the fantastic CS51 concept of recursion. How?
Are we allowed to use regular expression here?
All right, you are not allowed to use regular expressions. Regular expressions are a language that it can be expressed using the terms of this grammar language, but this grammar language can express languages that regular expressions cannot. I just taught you 121. Catherine.
So you could say letter 3 is equal to letter 3 plus a or b or c, and then somehow given that it's a word.
Somehow given that it's a word.
Yeah, given that the a's and parentheses.
Okay. So that is close, but it's not quite where we're going to get to in terms of the grammar. Here's what I would say. I would say that a word is either a letter or a word is a word immediately followed by another letter. Okay? So a non-terminal, one of these one of these symbols can be defined in terms of itself. So this is recursion, and I just taught you 51 as well. So why is the word, but a word? The word but is a word because the word be is a word because B is a letter. Okay? So since B is a word, BU is a word because B is a word and U is a letter. Because BU is a word, BUT is a word B-U-T. And then, should I add another T or not? Well, it's homophonic, it's ambiguous, but you know what I meant. B-U-T would go here, and then the additional T would go here. Okay? So this is a very clean way to define words in this grammar language. So, question, does this grammar define the same language? It's a different grammar. I'm assuming here that in both of these cases, letter is we're referring to letter by reference from the grammar above. What's your name? Franklin.
I feel like the answer is yes, but and I don't quite see why it would be no, but I'm getting the feeling that it's going to be no. But just by the virtue of the fact you're asking the question. It should define the same though, because it can define one-letter words and two-letter words and so on.
Franklin's answer is yes, except I think you mean no, except yes. Franklin is correct. The answer is yes. This is like, these are defining the same grammar, which we could figure out in this specific case by compiling both of these grammars to regular expressions and observing that the regular expressions were the same. But it is, I actually forget, because I'm not actually the teacher of 121, I think it might be impossible to tell whether two BNF grammars accept the same language. But it's certainly difficult. Someone should look this up. This is being recorded for posterity, my lack of knowledge of theory. It's fantastic. Okay. So this is, sorry?
I was just saying that the language is not decidable, but recognizable.
The language is?
That like decides whether two grammars are the same language.
Yes, so the language that decides whether two grammars are the same language is not decidable.
But it's recognizable.
But it is recognizable. So we can tell. Okay, fair. Great, thank you. Let's look at something that can't be done with regular expressions. I clearly don't want to go down that road, but we should go down that road at some other time. Maybe like after 9:15. The parenthesis language. So what we want with the parenthesis language is balanced parentheses. Okay, so every left parenthesis is followed by a right parenthesis, and they're balanced. Okay, so examples, that works, that works, this works. That works. These are not good examples. Not balanced. Not balanced. Not balanced. Okay? Help me out. Or ask me a question. Franklin has a question. Franklin has an answer.
I think you might be able to do something like parentheses, parentheses.
Okay.
One word.
Parentheses, parentheses. Okay. This language accepts no strings. It accepts no finite strings.
That's not all of it.
That's not all. I am terribly sorry. Apparently this isn't all of it. What else do we want?
So I think we also want like left, right itself.
Should we stop here? Why does this language not accept any finite strings?
Because if we look at the shortest string in here, it has to be composed of this and the smaller string and part of this. So since there's no shortest string, unless the strings are infinitely long, this will not accept any finite strings.
I buy that argument. That is like actually the kind of argument you would write down in a proof. A systems argument is that there's no base case. This is recursion with no base case. This is like an infinite loop, right? And since like a finite string has an end, we need to find an end. We need to find like at least some zero length string or finite length string that will be accepted by this grammar, and there isn't one. So we need a base case. So the question that I was hoping somebody would ask is, does 0 parentheses count as balanced? What's your answer? Okay. Well then, we have a base case. Now, there's all kinds of finite strings that are accepted by this grammar. But does it accept all of our desired examples? No, it doesn't. Give me an example of a string that it doesn't accept. Catherine. Parentheses, 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 parentheses. Right. Doesn't accept that. So we need one more case, which is parens, parens. So this language, I believe, accepts every possible balanced parenthesis string. Question how?
So does this grammar allow us to put like lighters inside the parentheses?
Does it allow us to put layers inside the parentheses?
Lighters, like A, B, C.
Letters. This does not allow us to put letters inside the parentheses. It does not. That's correct. So the language of Brown's parentheses is a very simple language. It is not a regular language. There's no regular expression that can accept balanced parentheses. It's one of the examples where it's very easy to write a program that very efficiently recognizes this language, but it is impossible to write a regular expression that recognizes this language. You can only recognize finite instances of the language, and that, the regular expression, looks terrible. And that is because this language is not context-free. You need some state to recognize this language more than a finite number of states in a regular expression. You need to know how many parentheses deep you are. Okay, this is sort of like a whirlwind tour of material that you'll see later in other classes. The reason that it's important to do here now is that this formalism, this grammar formalism, is actually something that's like part of the language of computer systems and computer science. Like every language that you use is defined in terms of a grammar like this, or has a grammar like this attached to it. And like, if you look into one of the founding documents of the internet that defines how, say, the web protocols work, you will find grammars that are written this way. So I think it's very useful. Although the grammar is like pretty intuitive to get, I think you can kind of like guess what it means just by looking at it. It's important to go through it. Okay, so how could we make this recognize a letter as well? We could say that you can have a word inside the parentheses. Okay. From this example of BNF grammars, let's turn to our BNF grammar for the shell. So this defines the grammar that this defines the language of the command lines that your shell will accept. And among the things that this BNF grammar does is it tells you how the different operators in a shell relate. So it shows you, for example, that redirections appear in a command. It tells you that pipelines are sequences of commands connected by the pipe operator, and that conditionals, which involve and, or, occur outside pipelines. So pipelines are sort of smaller than conditionals. A conditional connects multiple pipelines with a conditional operator. Okay, so there's a hierarchy that we're seeing here, where command lines are the biggest things, And then command lists are connected by semicolons or ampersands. And then conditionals are connected by ands and ors. And then pipelines are connected by pipes, and then commands are at the bottom. Okay, let me ask you a question based on this grammar. I'm just going to move this up so you can see the relevant part of the grammar. I'll also note that this grammar is written ignoring white space. So the assumption is that white space can occur between any of the tokens. So here's the question. Is this a valid command? Echo into F, hello world. Nobody writes commands this way. But is it valid? Catherine says yes. Anybody else? Why are you saying yes? It would replace the contents of F with hello world, that's right. But if you have any sort of familiarity with the shell, you never see these put at the beginning of the command, they're only put at the end. Like saying echo hello world greater than F, that's very common. Saying echo greater than F, hello world, very uncommon. But it's okay, because the grammar doesn't order words and redirections. It just says word or redirection, and there's more than, one or more of them. If you try this on an actual shell, you'll find that it works. And maybe it's only if you use Unix for 20 years and then look at a shell grammar that this shocks you, but I will tell you that I was shocked when I first saw it. But the grammar is telling you what's valid and what's not. Let's look at a particular example of an instance of that grammar. So this is a picture that's sort of explicitly showing you the hierarchical structure of a command line. That command line involves 6 commands, A, B, C, D, E, and F. They're joined into 4 pipelines, which are joined into 3 conditionals, which are joined into 1 command line, right? And that's the hierarchical order that the grammar shows. Command line, then conditional, then pipeline, then command. So the hierarchical order appears like implicit in the grammar. The question is, what command line string would correspond to this structure? So let's take a minute and think about that. Any questions or ideas here? Yeah, Gio.
Question. Could you explain background and foreground?
I could, but not right now. I'd rather do something else right now. I'd rather get through this example now. Let me give you a simpler example, okay? I'm going to draw another hierarchy. going to be super complicated. Your minds will be blown. Let's say that I had a command line that consisted of a single conditional, that consisted of a single pipeline, that consisted of a single command, where the command was echo hi. How would I write a string that corresponded to this structure? Catherine? Thank you, Catherine. Echo hi. Very good. Okay. Let's make this just a little more complicated. Let's say that I had a command line that consisted of one conditional, that consisted of a pipeline, where the pipeline consisted of two commands, where the first one was echo hi and the second one was less. How would I write a string that compiled to this command line? Adriana?
Echo high or less.
Echo hi pipe to less. Yeah, just one. In this unit, when I say or, I tend to mean the double or. But yes, absolutely right. So that would correspond to echo hi pipe to less. Okay. What if I had a command line that had consisted of a single conditional? The conditional consisted of two pipelines. The conditional was an and conditional. And the pipeline, the pipeline had one command in it, which was echo yo. So how would I write a string that corresponded to this? Echo high, thank you, Hao. Echo high, pipe to less, and echo yo. So you're getting a sort of a feeling for this, right? The structure is showing in diagrammatic form the inherent grouping that the grammar requires. Okay? This is just a string of characters, just one character after another. But those characters have operator precedence the same way that like an expression in math does. If I say a plus b times c, you know that you do b times c first and then add a to the result. The same kind of thing is going on here. If I say echo high pipe to less and echo yo, you know that you do echo high pipe to less as one unit and then apply and to the result, because and has lower precedence. Okay, now let's go to the structure that's shown on the board or in the diagram. So we have one conditional that's running in the background. It consists of one pipeline, and that pipeline has one command. The command is A. Since the conditional is running in the background, that is represented in shell syntax by an ampersand. Then we have two pipelines as part of the next conditional. The first pipeline contains B and C. B pipe to C. And then this conditionals are linked by the AND operator. The second pipeline just contains D. And that conditional is run in the foreground. So the operator there is a semicolon. Finally, we have a background process that has one pipeline in it with two commands, E pipe to F ampersand. So this is the command line that would give rise to this structure. Question, Shruti?
I'm kind of confused about like what pipeline means here. Like why does pipeline have to link the conditional?
Why does pipeline have to link the conditional into the command? So the word pipeline in this context refers to one or more processes that are connected by pipe operators. So one process is a pipeline. It's just it's like a degenerate pipeline. It's a trivial pipeline.
Yeah. In the previous example, we had like and like the double ampersand.
Yeah.
Yeah. Echo yo. Like,
Double ampersand, echo yo. Yeah.
since it wasn't actually a pipeline there.
You need a pipeline because the grammar requires it. The grammar appears to require it, right? The grammar defines the valid strings, and the grammar says it's a pipeline. There's a way, like, I'm not sure that you've ever done this, but like when we talk about mathematical expressions in terms of algebra, there's like, we throw around terms like there's expressions and terms and factors, right? Where like a factor is like something that you might multiply with something else. And a term is something that you might add with something else. But it turns out that every factor is also a term. And every term is also an expression. And something of that sort is going on here. A single command is also a pipeline, but it's just represented at a different layer of abstraction. Catherine.
Can you just explain why we have to put the semicolon
Why do I have to put a semicolon at the end of the conditional? So if you construct a command list by connecting multiple conditionals together, you have to do it with a separator, which is either a semicolon or an ampersand. Semicolon is used to separate, to say that the command on the left is a foreground command, and ampersand is used to say that the command on the left is a background command.
But then if conditional 3 was a background command, then why was there a semicolon after you said?
Sorry, I couldn't hear you.
Because for conditional 1 there's no semicolon, but for conditional 3 there is a semicolon.
Well, for conditional 1, there's an ampersand because conditional 1, the type is small, but conditional 1 is a background conditional. So you can see that there is a separator. It's the single ampersand. Okay, so this brings us quickly to Jiho's question, which is what is background? What does that mean? Let me show you. If you want to wait for 5 seconds, you run the command sleep 5. And then you wait for 5 seconds, and then it comes back. But if you want to wait for 5 seconds, but you don't actually care about what happens after you wait for 5 seconds, you sleep 5 in the background. You're just going on with your life, and then approximately 5 seconds later, sleep 5 exits, and we get told that it exited. So what background does is background runs a command, but it doesn't wait for the result. We'll see wait on Tuesday, so you'll get more about background commands then. But foreground commands, you wait for the result, you wait for the command to complete, you wait for the process to exit. Background commands, you just don't wait for them. That's what they are. Okay. So, if you were to sketch a set of C++ structures that correspond to this complicated design that we've laid out, then you are not alone. You are one of many students that we have had in this class. The students see the grammar, and they're like, okay, my code should look like the grammar. And they might come up with a set of structures that look like this. A command is something that has a vector of arguments, and it has a next to the next thing in the pipeline. A pipeline is something that has a command child. That's the leftmost command in the pipeline. And then it has a next for the conditional. And then a link that says whether that link is an or an and, because there's two kinds of conditionals. And then you say a conditional is something that has a pipeline as the first child. And those pipelines are linked by this next pointer. And then there's another next at this level for the next conditional in the list. And then there's a Boolean saying whether this conditional group is done in the background. Okay? And this leads to structures that look like the grammar structures that we showed you. You can make this work, and if this is the way your mind works, I encourage you to make it work this way. But this is far from the easiest way to make this work. Okay? The easiest way to make this work is to do this, where you just have a bunch of commands and you mark each link between them with the operator that's separating them. Okay? So rather than this picture, we have this picture. This is a pretty simple structure. A command has a bunch of arguments in it. It has a link. It has a next pointer, and it has a link that says what kind of next pointer this is. Is this an ampersand? Is it a semicolon? Is it an and, or is it an or? You store that information in the link. This is, in my opinion, much simpler to work with for many purposes. But it does make some things a little harder. How can you tell, for example, in this structure, whether the current command is part of a background command conditional? Up here, it was like kind of simple. You just looked at parents. Do you want to know whether C is in the background or the foreground? Well, you look at C's parent, and then you look at the parent's parent, and then you check whether it's foreground or background, and it's right there. Right? Here, it doesn't seem as simple. How do you know whether C is in the background? What do you do? Catherine? You could add an extra field to your struct. You could. You would then have to sort of go backwards as you were parsing the string and fill out that field for previous commands. I'm suggesting something different. I'm suggesting that you use exactly this struct, and let's not add anything else. How can you tell whether a command is part of a foreground or background conditional? Let's see. Steve. Check the link. Okay, so that is exactly the idea. You check the link. But you cannot just check this link. What you do is you step forward through the structure until you find a link that's either a semicolon or an ampersand. You just step forward. So there's a trade-off here that's like a time versus complexity trade-off. So in the version of the code where you have parent pointers, maybe that is more complex, but you spend less time traversing the command list. In this structure, it's simpler, but you spend more time traversing the list. The commands that we give you are not terribly long. No shell has to parse like 7 megabyte long command lines. This is a good trade-off, in our opinion. So the way that you would write this particular code is like this. So while the operation is not a sequence and it's not a background, go to the next pointer. And then it's in the foreground if the op is not background. You could do similar things if you want to test whether the upcoming conditional command is an and or an or. Franklin.
Should chain in background return, should that be equals?
That should probably be an equals, yes. Chain in background, and it's implementing chain in the foreground.
Is type sequence the same as like type foreground?
I think in our handout code there is no type foreground. It's type sequence or type background. But yes, type sequence means type foreground. Any questions? Okay, so there's a bunch more section material. Maybe we'll cover it in the optional section next week. But you can also just run through it on your own. These other putting commands together exercises help explain to you how conditionals are supposed to work and run through a bunch of examples with those. But if there's no more questions, that's it. Thanks.